Hi everybody, and welcome to our enthalpy of formation of magnesium oxide lab. In this lab, we are going to be using Hess's law to help us determine what the enthalpy or heat of formation of magnesium oxide is. All right, so the reaction that we are interested in this is the balanced equation for it. I'm actually in number 2 on your pre-lab. Number 1 is just a regular Hess's law problem that I'm going to want you to do and prove that you have watched those notes and you know how to deal with Hess's law. This is number 2. Write a balanced equation for the synthesis of magnesium oxide. In a moment, you're going to watch Maurice actually do this reaction where he takes a piece of magnesium metal and he burns it, and he's going to produce a white powder that is magnesium oxide. And this is the balanced equation for that. But if you notice, I write, make sure you have only 1 mole of magnesium oxide. Well, looking here, I have 2. But for the purposes of Hess's law equations, we need this to be a 1. No problem. If I needed 2 to become a 1, it just means I'm going to divide everything by a half. All right, which is going to give me, hopefully I can do this in camera. All right, it's going to give me mg plus 1/2 O2 is going to give me MgO. I know when we originally did balanced equations, I told you don't ever have halves, but in the case of these Hess's law problems, this is allowed. So this is what you're going to be looking at and trying to find later in the lab. So you're going to watch Maurice do this reaction. All right, and you're going to see that it produces a huge amount of light. It is an exothermic reaction, but it's really hard for us to determine how much energy that is. So instead of using this reaction directly, we're going to do 2 other reactions, and that's what you're going to watch him do. All right, and reaction 1 is going to be between magnesium metal and hydrochloric acid. You're going to write the balanced equation. You're going to go on ahead and write down all of the data. Reaction 2 is between magnesium oxide and hydrochloric acid. And again, you're going to record your data here. I want to take a moment and talk to you about how to deal with these calculations. So these helpful hints are incredibly important, and make sure, I will even put a star by this so people know to make sure they're looking at that. All right, because you're going to use a specific heat equation. And what you can do is you can assume that the hydrochloric acid that we were measuring the temperature of has the same density and specific heat as water. So please remember the density of water is 1 gram per milliliter. All right, 1 gram per milliliter. And then the specific heat you should know from this unit, okay? Also, you measured the length, or Maurice measured the length of the magnesium. You need to be able to convert from that length to a mass. Here is your conversion for that. All right, and you will need that in this problem. So for each of these, you're going to use a specific heat equation to calculate the amount of heat given off. Again, this is going to be your, Q is equal to mass times specific heat times delta T. In letter B, you're going to be using stoichiometry. Okay, you know how much magnesium you started with. You can solve to figure out, all right, how many moles of magnesium that would be. Same situation is going on down here. And then finally, the conclusion, I'm giving you 1 extra equation. So you're going to use reaction 1, reaction 2, and my given reaction to finally come up with your delta H for this reaction. All right, okay. And then finally, you will give me a % error, and I will let you know what that known value is at the end of the video. Take care.
Hi, welcome to our lab.
All right, so Maurice is going to take a piece of magnesium metal and put it into tongs. The reaction that we're talking about today and the goal of today is to figure out, let's take a close look at that magnesium, is to figure out the energy involved in the reaction you are about to see. We're going to be reacting magnesium with oxygen. Now we could just wait a very, very long time and let this happen with the air, all right, with the oxygen in the air, but instead we are going to burn the magnesium to speed up the reaction. So Maurice, go ahead. Okay, pull it out of the flame. I've got to go back in. I don't know what happened. Pull it out of the flame. All right, as you can see, this reaction gives off a huge amount of light. right, it is an exothermic reaction. We're going to come in close here. Now, Maurice, we want to just tap that on the lab station. See, we have turned this into, tap, 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 to a white powder. And that white powder is magnesium oxide. All right, it is a powder. Okay, great. All right, hi guys. So for reaction number 1, you need a length of magnesium metal. And so this is our piece of magnesium metal. I'm having it lined up to the 0 as much as I can. So you need to take the length of that and record it. All right, we are then going to react that magnesium metal with hydrochloric acid. Maurice has 30 milliliters, that's again 30 milliliters of hydrochloric acid, and he's going to put that into our calorimeter, which is a styrofoam cup, and he's going to take the temperature of that 30 milliliters of hydrochloric acid, and we're going to have to record that. So we're going to take a look. Okay, good angle there. Stop twisting it, please. Alrighty. And it is warm in the room today because our hydrochloric acid's pretty warm. Okay. So that is our initial temperature of our hydrochloric acid. Again, make sure that you record that. Maurice is now going to add the magnesium to the hydrochloric acid. All right, and we're going to see what happens to the temperature. You can hear, and we're going to go down just to see. You see the bubbling. We're producing hydrogen gas. We saw this reaction in one of our other labs. All right, hold that steady, and you can see, and we're looking for the highest temperature reached. Highest temperature reached. So we're going to keep just looking at that thermometer. You can see the hydrogen gas is giving off, and you can see that temperature rise. Okay, and we are looking for the highest temperature reached. I just twist it that way a little bit. Perfect, perfect. Good. All right, so. All right, now we're coming in and out of focus. So we're looking to record the highest temperature reached. So once that temperature starts going back down again, we know we have reached our highest temperature. And this reaction is giving off energy because it's increasing the temperature of the hydrochloric acid. All right. It looks like that is our highest temperature reached, okay? And if we look in, all of the magnesium has reacted, all right? And that is it for experiment for reaction number 1. All right, so we are ready for reaction number 2. In reaction number 2, we're going to take magnesium oxide. And remember, magnesium oxide is that white powder we produced when we burn that magnesium. So we're going to start out with magnesium oxide, and we're going to react that with hydrochloric acid. So we've already massed out in this Dixie cup exactly 1.00 grams. So again, 1.00 grams of magnesium oxide. Maurice is going to pour in the 30 milliliters of hydrochloric acid. And we're going to find the initial temperature of that. So, let's get you focus. There we go. Okay. All right, so there's our initial temperature of our hydrochloric acid. Okay, Maurice is going to add the 1 gram of magnesium oxide into the hydrochloric acid. And he's going to give it a little stir. We can already see some reaction happening. Great. And just as before, we're going to take a look at and see the highest temperature reached. So you want to...
Is that good?
Yeah. Cool. All right. We can look inside. Not a whole lot to look at, but our temperature is definitely going up. Let's try and get that in focus. There we go. Temperature is definitely going up. And we're just going to wait and see how high that temperature gets. Yeah, that's looking good. It's getting clearer and clearer. And we're looking for our highest temperature here. Okay, we just want to just give it one more stir. Okay, make sure it's all reacted. Okay, there we go. Let's get the temperature back in focus. Great. Okay, yeah, definitely going up a little bit more there. Okay, yeah. Let's give that one more stir. Again, this is the magnesium oxide reacting with the hydrochloric acid. Okay, yeah, we're definitely increasing there. All right, go ahead, Maurice, give it one more stir. The temp is still going up. We want to make sure all that magnesium and acid has reacted. Behind that 50 now, okay. All right, it's looking like that is our highest temperature reached, so we'll get a good zoom there. All right, great. Good luck with the calculations. Hi everybody, now that you have done your lab, you're going to compare your value to the known value, and the known value for the enthalpy of formation of 1 mole of magnesium oxide, and that's why you had to make sure that that balanced equation is for 1 mole, is negative 601.7 kilojoules per mole. So please make sure that you have your values in kilojoules, or you convert these to joules when you are comparing them. Negative 601.7 kilojoules per mole. Have a good one.